This is the final video on the series Coding the Machine. Now I've decided to finish this series here simply because in order for us to continue generating more and interesting and accurate algorithms, we really need to employ a floating point unit. So for example, the last video I did was on linear regression. But the linear regression would only work whenever it resulted in a line with a gradient which was greater than 1 or less than -1. So that is, we couldn't deal with fractional gradients. Now, we could actually deal with some fractional gradients if we used our fixed point number system, but the fixed point number system only went up to +128 and -128. So again, there would be a limit as to what we could do. So we're in a position now where we're starting to generate really nice and cool algorithms, and there are thousands of other fantastic algorithms there that we could potentially write on our machine. But we're never really going to get the full flavour of those algorithms, and we won't get them working completely until we've introduced our floating point unit. The fixed point number system and our integer number system has taken us this far. But really, to go any further, we need to get the floating point unit on. So that's going to be my focus over the next 6 months, to get the floating point unit and also the chordic algorithm built in to the machine. And this really will open up the machine and allow us to do real scientific and mathematical algorithms. So before I go, let me just give you a flavour of the floating point unit, and I'll show you what I've done so far. I have already designed a 32-bit floating point adder, subtractor and multiplier. I've still got to do the 32-bit divider and the square root. Now I've also taken the adder, the subtractor and multiplier, and I've generated a 16-bit version. So these 16-bit versions are built in Logisim and they're ready to implement into our 16-bit design. But I have to generate the division and the square root before I can continue on. But once those are done, then we have all of the sections, and I'll be able to put all of the sections into the full floating point unit, which I can then implement into the machine. So I'm not starting from scratch. A large portion, probably about 60% or 70% of the work has already been done. So just to show you here, I have a spreadsheet and I generated this in order for me to help me work through the actual design and also help any students. So I've got in here different tools that I've generated. So for instance here, this is one which will go from a floating point binary to a decimal conversion. So you can stick in the floating point numbers here and you'll see it goes through the conversion. So this set of ones and zeros is equivalent to 1.474 times e to the -38. Okay, so that's a handy tool for that conversion, and it helps us to understand how we convert from the binary into the decimal. And we have the same thing generated for the going the other way. So we want to, in this instance here, to go from 5.7. In fact, it's in this instance here, we enter it down here. So say for instance 5.7, and then it generates the floating point number up here. Okay. And we've also got another tool here which is useful for generating both of them and going from 32-bit to floating point to decimal and then the decimal back, and you can see the differences. So for example, in 32-bit floating point numbers, the number 0.1 is not an exact representation, okay? It just goes on forever and ever. Now, if we want to, we can then generate this here by clicking on the same ones and zeros, and you can see it's going to generate the actual value. So rather than generating the value 0.1, it's 0.1, and we've got this at the end, okay? So we've actually got an error, and that's the error due to 0.1 not being an exact value in 32-bit floating point arithmetic. So that's quite handy. And the other two tools are the multiplier. So we can multiply the numbers together, and you can see it gives us the output. So we've got the 32-bit floating point number for this value here, and the 32-bit floating point number value for this here, and it multiplies up to this number, and this is how it is represented in 32-bit floating point. Okay, so granted you won't understand all of this here at the moment. Also in the background, whenever I go through the multiplication, there's an actual multiplication tree here that it works through, so you can see exactly how it all works. Now finally we've got an adder and subtractor, and again we can add and subtract the numbers, so points and okay, so just random numbers, and you can see here it goes through the addition and subtraction, and we can do the subtraction here. So it's quite a powerful tool which allows us to understand exactly how the floating point addition, subtraction and the multiplication, and eventually I will add in the square root and the division into this as well. So what I have to do is I have to take this, which is 32-bit, and generate a 16-bit version, okay, and I have to generate the 16-bit version for the divider and the square root. So once that's done, we'll have all that together in the Design a CPU 4 course. But I won't get into all the mad detail within the floating point unit because there's an awful lot in it, but I will give you a good flavour of how it all works. And if you're interested, you can take the full 32-bit floating point unit courses if you want to get into all of the detail. Now I will also add in the chordic algorithm as well, so we'll have a chordic method of generating a lot of our functions, and that will be quite interesting. So that's where I am now, and that's where we're going to go over the next few months. So thank you for listening. I'll get you on the next video. Goodbye.